on first-order methods for distributed network optimization by Angelia and Nedich. I hope I got that right.
Okay, thank you. I will present here some distributed model for optimizing a network where I'm not really as much concerned with communications, which most of the people here have been focusing on. So one can reiterate and consider the aspects of that issue. So the idea here would basically be if I have a collection of nodes that are given in some spatial they're given in some space. Each of the nodes may have its own objective function that needs to be optimized. And nodes might be connected in some network. I don't have a picture for this, so I'm going to lay down in plain words. And the objective of the network itself is to minimize the sum of the objectives given to the nodes. Nodes are not allowed to share the objectives, but the network is used as a basically medium for diffusing the information that the whole system can perform in a desired manner. So what do we mean by this is basically in the network there will be no central entity. There's no central node that will collect all the information relevant to computations. So there is no master-slave scenario. There is no access to the information from one spot. There are various reasons why we might like to consider that. I'm not going to go into great detail on that, but what I would like to bring into this setup is the fact that network itself, the communications could be changing over time. So couple basically possibilities are maybe the network is really static, but due to some kind of protocols we are running, not all nodes talk to each other at a given instance. That would give rise to a time-varying connectivity of the agents or the nodes. So the goal is, as I said, that we want to in a completely distributed manner, in a sense that every node can operate only locally, talk to the neighbors. We would like to design protocols that will be robust to the changes in the environment and also easily implementable. The simplest case, it's also drawn very often as a very simple kind of a setup problem, is that if we have a network in which, let's say this is a network where each node may have actually be associated with some collection of data and perhaps files, and each node knows its average file. You would like to kind of design a protocol that nodes can talk to each other and compute the average of the whole network, which can be cast as a simple optimization problem, as laid out at the bottom here. And the main point being that here theta i's are the average files that only theta I is the size of the average file that only node I knows, and it's not willing for whatever reason to share it. May not be a kind of a particularly interesting when it's kind of this kind of setup, but theta I could be something else. If it's a simple average file, maybe they can exchange it. But I'm pointing out that basically I would like to do this computation not knowing theta I, other than value is known only to node I. And then some algorithms for doing that have been proposed. And one possibility basically that is maybe of interest to this community is when problems of that kind can be also embedded into the support vector machine kind of problems. In principle, centralized, I have a centralized problem where I'm laying down constraints explicitly. In many applications or models, these constraints are typically penalized and brought into the objective with some kind of rescaling. But in principle, this is the problem we are facing. Originally, the points are actually within the constraint set. And one can fragment these constraints, basically turn them into centers, when each node will now, to kind of feed it into this framework, basically it can have a rescaled version of this norm of x, which is really like a regularizer here. And only dealing with these crossings or slacks of the constraints that node particularly has knowledge of, so that it deals only with a subcollection of the sets. In this case, the objectives is distributed, but also the constraints are distributed if one wants to look at this as a distributed problem. And here we would not allow, for example, nodes to exchange the data points, which means they're not going to exchange information that is embedded in xi, nor they're going to exchange directly information that is embedded in their objectives, but rather some kind of estimates. So what have been considering, I'm going to get to a brief overview of this consensus protocol and how that protocol have been used to kind of solve this kind of distributed problems. So consensus problem, which is basically a very old problem, had considered a case where you might have a set of nodes, and each of them has some initial value. In the most general setting of the problem, the goal was to design a protocol that will allow nodes locally to talk to each other, exchange some values, but not necessarily the initial values, and then come up with a protocol that will, in time, produce basically asymptotic convergence to a same point, which is basically alignment of the network on the same value, starting from perhaps different initial values. So there are two versions of this problem. One is exact averaging, where you want to really this limiting point x to be the exact average of the initial points, which is known as average consensus. And there is a more relaxed version where you just want to agree on a point, but you don't care what that point might be, just any point, which is a rather loose statement. So what this basically says, that if I have a kind of intuition that was driving us here, is that if I have a protocol that can align to a certain value, perhaps we can push this value into the place where we want to go. For example, if you're optimizing, then you might be pushing this point of interest or point of alignment to some pre-designed objectives that the network might have, by basically playing with this consensus protocol as an underlying mechanism to diffuse the information that you might like to see, that you don't know, but you want the network to know. So it turns out that, and you can come up with a couple of ways of defining this mechanism for the diffusion, is basically saying that if we define, perhaps the network might be changing. So let's say defined by n sub ik here to be the set of neighbors at a node I at time k, then what you are doing is you are receiving these values from the neighbors, and you are convexly combining them. This here embeds just basically averaging locally at a node I. Now, under certain conditions, here you can write, basically you can embed this into a kind of a linear model. This is just a dynamics at a node I, but if you set these values to be 0 for those who are not neighbors, you come up with a linear dynamics. And under certain conditions on these networks, you can guarantee that consensus is achieved. So the conditions had typically called for graphs to be, let's say if they are directed, to be strongly connected. The matrices to be row stochastic, basically matrices that you are constructing by putting these weights into the matrix form and zeroing out the neighbors that are actually nodes that are not neighbors of a node I for any node in a network. You can come up with basically the matrices become row stochastic. And but one of the typical conditions that were needed for convergence of this protocol had to do with requirement that the nodes basically if a node is giving a weight to its neighbor, then that weight has to be persistent in time. It can basically saying that there should be some positive constant so that all positive entries have to be uniformly bounded for all the nodes and at all times. And that was kind of, in essence, mechanism to ensure that information is properly mixing and not losing over time. So key part that was relevant to if you want to do anything else on that kind of network, whether you want to optimize, whether you want to perhaps consider some kind of other control problems, or perhaps you want to consider even some particular dynamic of what may be associated with some social networks. The key element there for the analysis of anything else you want to build had to do with really the fact that when you're looking at the rate at which this mixing is happening over the network, the convergence rate is geometric. Now, the word geometric is nice. What we mean here is that really what some people refer to linear convergence. Basically, for example, here it says that this, basically if you look at the spread of the values of any two nodes in the network, so the max and min, are decaying with some factor proportional, basically beta to some factor raised, but the important part here is that it's really decaying with time. Beta is a parameter less than 1. However, this parameter itself need not be favorable. What I mean by that, if the beta is very, 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 very large or very close to 1, you have a very bad mixing. So different now opening different structures in the network can reveal much better constants. This is the worst case scenario. So basically, this is very generic setting and very, 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 basically, constant is extremely loose because it covers all possibilities. So what I want to overview now is just briefly what we've done with this problem, basically how we use this to optimize, and then in principle there was one kind of key assumption we were making that we wanted to remove, and this is the one that I'm going to focus much more in a few minutes. So if you want to optimize, in this case, I'm going to skip here faster because I'm running. One possibility to do this is basically, so they optimize this function over a network. Let's say they have some commonly known constraint. Every node can work only with its own objective function, fi, and it can exchange estimates. So I'm assuming here that it estimates a finite dimensional, possibly vectors. So this can be achieved within operating in 2 steps. In a synchronous model, every node will first collect information from the neighbors and mix it. This is like intermittent step, and we are basically looking at a consensus-like step that aligns the nodes in the network. And the second step is really pure projection at each node, where each node just takes this intermittent estimate, the mixed estimate, and pretends it's only minimizing its own objective function. So the only interaction of the nodes is here when they're making these convex combinations. Now, under certain conditions, I'm going to skip this. It can be ensured that such algorithm would converge to an optimal value of the overall sum function. How can that can be done by basically laying down the conditions that are pretty much needed for consensus to happen, and typically conditions you would need for algorithm of that kind to converge. So here, if I'm not assuming that the functions are, let's say, differentiable, I use the notation of the gradient, but I'm burying in a possibility that these are subgradients, then what we typically require that these subgradients are bounded. If I worked with the Lipschitz, I would require, or differentiable functions, I would require some kind of Lipschitzian growth of the gradient for the gradients, and then or linear growth for the gradients. And step size is here also kind of what is considered the slow, but it's the one we need for convergence because of the network kind of impact. There are a lot of errors in the system. So you're working with a very erroneous gradient method, and these kind of step sizes are needed to kind of ensure stability of the process. Now, the graph assumptions are typically, if I assume here that graphs are only strongly connected at every instant, just to make it somewhat easier, requirements are still same as this kind of a persistent mixing with a positive weights for all neighbors and at all times. It's really this persistency conditions for the diffusion to happen. But the critical assumption we were making here is that the matrices were doubly stochastic. And that was the critical for ensuring the statement that the iterates that were generated locally by the nodes would converge to a solution of this problem. The summation of the, summation of this. If the weights were not doubly stochastic, we would here see basically scaling pi I times fi, where pi I has to do with some limiting steady state vector of this matrix product convergence. So I'm going to skip that. This was just illustration, but I'll leave it out. So to summarize, because I want to go to the main kind of extension that has to do with removal of these doubly stochastic weights, is that critical assumption was that we have doubly stochastic weights on a supposedly directed graph, right? I was assuming directed and strongly connected graphs. And this is one of the problems that cannot be solved in real time. It's very complicated. and it's basically a very complicated problem to even determine such weights on the graph. So what we had looked recently, that came after discussion with Mike and and his students, that resorting to a different consensus algorithm, which was motivated by work by Urbana-Champaign and Gerke, they are considering some kind of linear iteration algorithm to do that. So for the basic consensus part, linear iterations assume some kind of this form. So what do we here have is the graphs are changing, and this sub j of t is the degree of a node j, including itself. So then this is out degree. So every node knows how many nodes it can contact on its outgoing links, and that's dj, including the fact that it can talk to itself. And this can be considered as xi of t is actually trying to estimate what's the total sum of xi's at a given instant of time. So what's the sum of our values at a given instant of time? The next term is almost as node trying to estimate how many nodes are out there on the network. So initially, it's critical to set this value yj at time 0 to 1, because at that instant, node only knows about itself. So this is more like counting or estimating how many of us are in the network, and this is saying what's the total sum of the values we have. And the true value, the variable z, which is formed by actually ratio of these two variables, is the one that is going to go to the consensus. This is going to go to the initial average under certain conditions. So when the node, what is the node doing here at any instant of time? Node will have some value, let's say xj. I'm looking at node j, or at node xj, and at the time now it has value xj of t. That node will look down at the instant when it needs to compute. It can look at outgoing neighbors and send them this information, basically. Its value, current value divided by its out degree. It sends to every neighbor that it can reach through outgoing links. And it reserves also that value for itself. Now, node xi is here, the downlink neighbor who does this mixing from that information incoming from the. So node I will receive that information from all of its incoming links and form this. And the same goes for yj. It's just another variable that has to be kind of combined in the same way. And then the main difficulty with the analysis of this algorithm is that the matrix that you can construct now by looking at these weights in the process turns out to be column stochastic. So it's not, in the prior case, it was row stochastic. Now it's column stochastic. And there is a slightly more kind of complication involved with the analysis of those, because for them we got weak ergodicity but not strong. And then the whole hurdle we had worked here is to actually check what's the rate, where these matrices are going. And it basically turns out that by using some kind of basic linear algebra analysis, we can estimate what's the difference of this estimate of the average from the true at the time average of the system. And that is driven by some expression in which there is term that decays geometrically, and there is term I considered here like erroneous kind of case when we have a shift with some error. So there is a term that depends on the error. The purpose of this error is actually to bury later if I want an optimization problem, or perhaps I want some control problem. So this is the drift with some field I can induce from outside. It's kind of on a top of the network, I can induce another field. And as long as that, because we are usually controlling this with a step size, this is some kind of small, in a sense small after some time. Therefore, what turns out that the critical two values for the mixing process are these delta and lambda. Again, we are looking at a very generic case. So our predictions here are the worst case possible. One can look at the particular details and find out models for which this might, the estimates could be better. Intuitively, lambda is something that comes from the network. Basically, could be related to this second eigenvalue if this was Laplacian or something like that. A delta here is something that's not seen in the in the prior, in the first model as much. Delta has to do with kind of influence distribution among the nodes. What this means is, imagine that at an, initially you give each node in a network power of 1. And after this mixing of the matrices, it goes from, let's say, A0 to, so from AT to A0, where you have now column stochastic. This is basically a form of a distribution that will happen at the end of the time t through these matrices acting, product of the matrices acting on this initial power equal to 1 everybody. And the delta is the smallest power that agent would have in a network. Basically, the smallest value that you would get from letting product of AT to A0 act on a vector of all ones. So for the particular networks, one can compute this. In a simplest case, if this is just a simple analogy, if this was the doubly stochastic matrix, that the power stays the same, because the matrices will be row and column stochastic, so it doesn't matter. To summarize, I'm going to just go to, this is a list of all the relevant work, a lot of work by Rabat and his friends. What we can show is that under assumptions that the graph is uniformly strongly connected, here the degree helps us to remove this requirement of uniform lower bounded kind of entries. So under assumption of subgradients being bounded, you can guarantee that they all converge to a same point. Again, we are optimizing the sum of the objectives. And we can also provide a rate which says that in the case of a rate here, we are using first the step size that is proportional to 1 over square root of t. And then to provide the rates, we are actually not using the z's that the agents are generating, but rather we are basically constructing the averages of these iterates over time. And the weights that are used for these averaging have to do with the step size choice. We have seen these constructions in, I think even that the dual Nesterov method would also use something like that. So at the end of the day, we can show a bound, which at most interesting, I would say, the rate is here. Actually, a couple of these terms depend on the ln of t over square root of t in a very generic, no special structure network, no special structure function. So this is very similar to the rate that Ducci, Agrawal, and Martin Weinreich had in their dual averaging implemented on the network as well. And this is coming, ln of t comes from the mixing of the network that we cannot, there is a particular kind of expression that if one can do better estimate there, it can remove these ln of t dependencies, but we couldn't do it this far. And this 1 over square root of t is just a byproduct of the fact that we are working with subgradients with no special structure on the problem. One can tighten this result for strongly convex, but the only thing that changes is here. Wherever square root is playing, you can get 1 over t. But ln of t, we were not able to eliminate yet. So as far as the communications go, this is certainly, meaning this itself is more easily implementable in asynchronous manner, because the way the nodes communicate, it could be broadcasted simply. So it's pure broadcast to downlink neighbors. And you don't, even though where I wrote it is, the triggering or the computations appear to be at the same instant of time, you can easily imagine that nodes are not doing anything, which amounts only to the mixing time that might have changed a little bit. So what I'm trying to basically summarize here is that communications here are by far reduced, and synchronicity is not the key. You can come up with the algorithms that are totally asynchronous, basically by having a random, each node has a random clock. As long as these clocks are aligned, even the step size here that we kind of aligned can be also taken out. There is a way to basically base this step size on the number of times the node had woken up. And asymptotically, that would kind of behave no different than this. So you can relate those two, except that it will take definitely this analysis here will apply to expected values, and then you have, one has to worry about perhaps checking out what's the variance with respect to, or probabilistic bounds that I can give on the how long I need to wait for this to drop down to, meaning like Chebyshev type of analysis can do that. So in principle, I think that maybe something here of interest to this community might be, because it is possible to look at the communication complexity, which we haven't done. And it's better than the one when we looked at the averaging with the convex combinations. And I will leave it at that. There is, we have a report on this, and we had some small simulations here. This is not as exciting. We just take a simple each node got a quadratic function, and basically we are computing an average. So you have x minus theta I. And this is just the behavior of the iterates of maybe one agent in network of about 1,000 nodes. Here we had something different. On this line, we have how many iterations we need for some criterion to be satisfied. On the y-axis, we have the growth of the network size, which goes from 1,000, 2,000 to, I think, here about 8,000, 9,000 nodes. So we were increasing the number of nodes using this, basically giving randomly assignments of these quadratic functions to the agents. And we took as a criterion, what we count here is how many iterations we needed for this system to compute the average within an error, let's say 0.1. So it's not a high error requirement. We were more interested in looking what's the tendency of how this time for the accuracy would grow as we exploding the number of nodes. And to be honest, I'm not quite sure if this is a linear growth or it's square root of n, because I think we don't, just this segment of the curve does not give me at least intuition which of them is happening. Alex thinks it's linear, but I'm not sure, unless we have something on a kind of a theoretical side. And with this, I'm basically concluding, and I'm thanking you for staying till the last moment. Thank you.
Questions? Oh, sorry.
So ordinary gossip algorithms are robust to small noise in the message passing.
Okay.
If you do push some and you're taking quotients, is this still true, or
Okay.
have you studied that issue?
No, we haven't. We haven't. I think, okay. Because what the analysis is doing, it's really independently looking at the evolution of the numerator and the denominator. So I would think that I'm not sure where the variance will hit us, because in the expected sense it's not touching us, but when the variance kicks, then there will be coupling. And I think there could be some, meaning, I believe under certain conditions you can get it out. Because the truth is, it's really evolution of these two independently. Only at one place they couple. So I think it's doable. But we haven't done it.
Questions? Thank you very much.
Yeah, thanks.